Hello, my name is Orion Ning, and today I'd like to talk about my work with Kailash Raman and Ben Safdi on cosmological neutron stars produce diffuse axion X-ray signatures. Our headline result is that we derive new stringent constraints on axion coupling parameters from the non-observations of a diffuse axion signal predicted from the cosmological neutron star population, or all neutron stars produced throughout all cosmic time. Here, we show the results of our two main searches. On the left, we show the 95% upper limits on the combined axion-nucleon and axion-photon couplings from searching for ultralight axions converting to X-ray photons in neutron star magnetospheres. And on the right, we show the 95% upper limits on the axion-photon coupling from our searches for heavy axions which undergo delayed decays to detectable X-ray photons later in cosmic time. Note that in the heavy axion case, we operate under the assumption and motivation of a heavy axion compatible with grand unified theories with no tree-level couplings to quarks, which allow us to interpret all constraints in terms of the axion-photon coupling, as shown here, within this model using our benchmark anomaly coefficient ratio of E over n equals 8/3. Excitingly, in the ultralight axion case, we are competitive with the extremely stringent constraints imposed by supernova 1987A, and we completely exclude the axion hints suggested by observations of the Magnificent Seven set of isolated neutron stars. For heavy axions, we are able to exclude large portions of new, never-before-probed axion parameter space for masses a few orders of magnitude around a keV, narrowing down the possibilities of heavy axions compatible with grand unified theories. Our search for axions among the cosmological neutron star population is shown in the diagram here. We expect the cosmological population of neutron stars to source a diffuse axion background, coming from the aggregate contribution of thermally produced axions from neutron star cores, mainly either through nucleon-Bremsstrahlung processes, or, in the case with superfluidity, Cooper pair breaking and formation. In the upper half of the figure, ultralight axions are light enough to efficiently convert to photons in the neutron star magnetosphere. In the lower half of the figure, heavy axions instead undergo delayed decays to two photons at some later cosmic epoch. The results are X-rays with a unique predictable spectra sourced from these neutron stars across cosmic time, with signal strength determined through the axion-nucleon and axion-photon couplings. Very briefly, we describe the ingredients that go into this diffuse axion-induced X-ray signal. First, we calculate the expected axion emission from nucleon-Bremsstrahlung and PBF processes over our neutron star ensemble, which also takes into account the neutron star mass distribution. Shown here are the expected axion spectra from these types of processes for our particular neutron star model. Then, we incorporate cosmology, that is the rate of neutron star formation over cosmic time, illustrated here. In the case of ultralight axions converting in neutron star magnetospheres, we also model the magnetosphere distribution over our neutron star ensemble, two examples of which are shown here. And all of these things combine to give us the cosmological neutron star axion-induced X-ray signal, which we illustrate for various ultralight masses here, and which we can go search for in cosmic X-ray background data. We also vary and analyze other ingredients, such as superfluid models, equation of state models, and more in the details of our paper. So we search for these axions, which give a unique photon spectra illustrated here, in data measuring the cosmic X-ray background, focusing primarily on NuSTAR observations up to around 20 keV, but also examining other telescopes like HEAO, SWIFT, and Integral, which go to higher energies on the order of around 100 or 200 keV, with higher systematic uncertainties. All of these telescopes roughly give comparable results in terms of axion constraints. In conclusion, we do not observe either ultralight nor heavy axions in cosmic X-ray background data. And the absence of this diffuse signal allows us to set very stringent constraints on axion couplings across large axion mass ranges, as you see here. We detail more variations and searches throughout our paper, including the exciting potential of future telescopes to reach new parts of ultralight axion parameter space closer to the QCD axion lines, from better observations of the diffuse neutron star axion X-ray background explored in this work. Thanks for listening, and we hope you check out our paper.